This question is meant to give us some practice with working backwards in a reaction. So the question says, which of the following substrates below will produce the indicated product as a possible major or minor product in the indicated reaction? So in this case, we're given the product and we're given the reagent and solvent, and we have to think kind of backwards and think, all right, what could our starting material, our substrate, possibly have looked like? So again, my strategy for this is to usually like analyze the answer choices a little bit first, the different substrates, and then I'll take a look at the kind of official answer choices on the left-hand side of the screen last. So I'm going to go ahead and start writing. So the first thing I'm going to do is think about what type of a reaction is this. In order to kind of tell what the mechanism is, we're going to have to examine the reagent and this product a little bit. So right away, we can see that we have an alkene product. So that is a dead giveaway that an elimination has happened. So E1 or E2, just based on the product that we made. If we take a look at our reagent, that'll be another big indication of which mechanism happened. So we have sodium methoxide, which is a small, strong because of the negative charge on the oxygen, nucleophile / base. So we know in this reaction it's acting as a base because we make an alkene product. So strong is kind of the key here. That typically favors a bimolecular process. We can also take a look at our solvent right here. The solvent is aprotic, so polar aprotic. And polar aprotic solvents also favor bimolecular processes. So the mechanism for this reaction is E2. And that's really important because E2 is a concerted process, which means the beta hydrogen is eliminated at the same time as the as the leaving group. And so everything's occurring all at once simultaneously. If we had an E1 process, then we might need to worry about carbocations forming and carbocation rearrangements occurring. With E2, on the other hand, we have to think very carefully about stereochemistry. So kind of different scenarios to consider based on which mechanism is occurring. So now that we know it's E2, we know that we have to have an alpha carbon that's attached to a leaving group, and we know we have beta positions. So I'm going to take a look at my product right here, and I'm going to kind of think about what possible molecules may have made this. We know that the double bond is always going to be between the alpha and the beta position. So I could label it like so, or I could label it like this, where this is the alpha and this is the beta. So it's kind of two different carbon atoms that could serve as the alpha. And that's important based on kind of the molecules we have to choose from. If we are kind of thinking about this, I'm going to number these. This is number 1, this is number 2. If we're thinking about structure 2, then the alpha is this carbon right here. And that actually lines up really well with structure number 4, where we've got the alpha carbon right here. And then the beta position is right over here. And we would have taken one of the hydrogens here in order to make a pi bond between that alpha beta bond. So structure 4 is a legitimate choice here. It could have produced that tri-substituted alkene in an E2 elimination. Next, let's look at answer choices 1, 2, and 3. Answer choices 1, 2, and 3 would have to come from the molecule that the alkene that we labeled as 1. Because in these cases, the alpha is attached to the bromine in this case, and the beta would be to the right of it. Molecules 1, 2, and 3 have kind of multiple beta positions, so they could have other products as well. But the other products aren't really important to answering this question. So I'm going to kind of remove those beta positions because we don't have to worry about them. So the key idea for E2 is that we need to have an anti-periplanar arrangement of the leaving group and the beta hydrogen. And so that is a big concern here. So let's draw in our beta hydrogen and what it looks like. So in molecule 1, the bromine and the hydrogen are already anti to each other. In molecule 2, the bromine and the hydrogen are not anti at the moment. We would have to rotate the alpha beta bond. Same idea with bromine and hydrogen on molecule 3. not anti. They're on the same face because they're both dashed. So in the two cases where we have not anti, that means that this alpha beta bond would have to be rotated in order for us to get that hydrogen to be in the anti position. And this is kind of the key to answering this question. If those bonds had to be rotated, then the product that we would make would look like this. So we'd have Br, and then when we rotate around, our hydrogen would be dashed, and this would be wedged, the methyl. And same idea over here in molecule 3. The Br is dashed. The hydrogen would now be wedged, and we'd have the methyl dashed. So in this scenario, the bromine and hydrogen are now anti. But very importantly, the alkene that they would make does not match the answer to the predicted product for this reaction. In these two cases, both in 2 and 3, we would make the alkene that looks like this, where the 2 ethyls are on the same face. And that's not what we have up in alkene number 1. We have the 2 ethyls on opposite faces. So this is very important. It allows us to rule out 2 and 3 as possible products of this, or possible substrates, sorry, of this reaction. Because we'll never have the beta hydrogen anti and have the 2 ethyls opposite in the product, because we have to rotate that bond to get the bromine and the beta hydrogen anti to each other. When we rotate the bond, the 2 ethyl groups become on the same face as each other. And so there's no way that we could make the alkene that's predicted in this reaction. So 2 and 3 can be crossed off. If we take a look at molecule 1, here we can definitely make the right product because the bromine and the hydrogen are already anti to each other. So the alkene that this would make doesn't require bond rotation, and we would make that alkene as our product, which is the product for this reaction. So 1 and 4 are both legitimate substrates. So let's take a look at our answer choices over here on the left-hand side. For the answers, we have 1 only, 2 only, 4 only, 3 and 4, and 1 and 4. So based on the analysis that we've done so far, our answer is E. Both 1 and 4 could make the product that we want to make in this reaction. So that's just kind of how I think backwards a little bit. It's a difficult thing to do because you have to assess all of the different kind of parts of the reaction. And E2 itself is just very detail oriented. There's a lot of little things to keep in mind. So don't forget about antiperiplanar. It's also really important in rings. So in this example, we looked at kind of an acyclic molecule that's not a ring, but in rings, you always have to have the leaving group and the beta hydrogen anti as well. So again, kind of my strategy for doing this was to just work backwards and think about what possible substrates might make these products, and then to look at my answer choices. And that's how I was able to solve it.